Welcome to the Explainer. Okay, let's dive straight into demystifying a classic and honestly kind of complex coding challenge. Today, we're going to look at exactly how to find all words on a board. We'll be breaking down the logic from the most basic human intuition all the way up to a highly efficient, fully optimized algorithm.
Here is our roadmap for today. We'll cover the word search problem, the single word approach, the multi-word bottleneck, enter the trie, the optimized algorithm, and finally, time and space complexity. Section 1. The word search problem.
First, let's establish exactly what it is we're trying to solve here. We are given a two-dimensional board filled with characters, and alongside it, an array of specific target words. Our fundamental goal is to find all the words from that array that can actually be formed by tracing a path through the board.
The crucial point here revolves around the rules of movement. We can only connect adjacent cells, meaning we move strictly horizontally or vertically, up, down, left, or right. We have to trace a continuous path to build our word letter by letter. But, and this is a massive but, the absolute most important constraint is that we cannot use the same cell more than once for a single word. Once a letter on the board is used in our current word path, it is strictly off-limits for that specific word.
Section 2. The single word approach.
It's always best to start simple, right? Before we start worrying about an entire dictionary of words, how would we go about finding just one single word? Let's say we're looking for the word stare. Our intuitive human approach is to scan the board for that first letter, S. Once we find it, we kick off what's called a depth-first search, or DFS. We literally look left, right, up, and down for the next letter, T, then A, then R. But suddenly, we hit a brick wall. We have STAR, but there is literally no E in any of the adjacent cells to finish the word.
Now, when we hit this dead end, we obviously can't just give up. We have to use a technique called backtracking. This means we essentially reverse our path. We step back from the R to the A. And we ask ourselves, okay, are there any other directions from A that we haven't tried yet? By backtracking to the R directly below the S and exploring a completely different route down the board, we successfully find the full word STARE. So this perfectly validates our intuitive DFS approach. For a single target word, exploring paths and backtracking when you hit a dead end works brilliantly.
Section 3. The multi-word bottleneck.
But as with pretty much everything in computer science, we have to ask, what happens when we scale this up? Think about it. Our dictionary array doesn't just have one word. It might have dozens or even thousands. What if our array contains both the word bite and the word bites? Does our single word start from scratch approach really hold up?
Well, this scenario completely exposes the fatal flaw in our naive approach. Imagine we just successfully traced the entire path for bite. To find bites, our basic algorithm forces us to restart the entire search from scratch. We have to find the B again, then the Y, T, and E, just to check for that final S. When you have overlapping words sharing the exact same prefixes, constantly restarting creates a massive, computationally expensive bottleneck.
Section 4. Enter the trie. We clearly need a magic tool to remember paths we've already walked. And this brings us to our absolute hero data structure, the trie. A trie, sometimes pronounced tree, is a specialized tree-like data structure specifically designed to efficiently store and retrieve strings that share common prefixes. Instead of searching for byte and bytes as totally isolated missions, a trie allows us to search for multiple overlapping words simultaneously without ever needing to restart. Think of it this way. We're essentially taking the chaotic, unstructured 2D board and guiding our search paths using the highly organized map of the trie. We just load all our target words into it. Now, words like bite and bytes share the exact same branch, all the way up until that final S.
Section 5. The optimized algorithm.
Let's marry these two concepts, the depth-first search on the board and the structural map of the trie, into our ultimate optimized algorithm. To properly execute this, we iterate through every single cell on the board. If the character matches a root child in our trie, we start a recursive DFS. And at every step of that DFS, we strictly follow these 4 precise steps. 1. Check if our current spot in the trie marks the end of a word. 2. Mark the current cell on the board as visited so we don't accidentally reuse it. 3. Recursively explore adjacent cells, but only if they match the children of our current trie node. And 4, when we hit a dead end, backtrack by marking the cell as unvisited again.
It's really cool to notice how elegantly this plays out in practice. We traverse down the tree and the board at the same time. We find B, Y, T, E. The trie node for E tells us, hey, bite is a full word, so we add it to our results.
But we don't stop and restart. The trie tells us, keep going. There's a child node S. We check the board, find an adjacent S, and effortlessly add bytes to our results in a single, fluid pass. There's literally no redundant searching required.
We do have to be a little careful, though. Remember step 2 of our algorithm? It was about marking cells as visited. Without meticulously tracking our visited states, our DFS could easily accidentally loop back on itself, violating our core rule. If we're at I, we might check our adjacent cells and accidentally reuse the T cell we literally just came from. We can brilliantly solve this by temporarily modifying the board right there in place. When we step onto a cell, we just change its character to a hash symbol, or honestly, any special character. This acts as a breadcrumb. If our search tries to look back, it sees a hash, not a letter, instantly preventing the loop. Then, crucially, step 4 reminds us that when we backtrack out of a cell, we revert that hash right back to its original letter, leaving the board absolutely pristine for other search paths.
Section 6. Time and space complexity.
Okay, let's tally up the final bill. What is the actual complexity of this solution? Breaking down the math. Time complexity is big O of n times L plus m times n times 3 to the power of L. Let's unpack that really quickly. Building the trie takes n words times L maximum characters. Then, for the main search, we check all m times n cells on the board. From each of those cells, we explore up to 3 directions, since we obviously don't go back the way we came, for a maximum of L steps. Now, for space complexity, that's big O of n times L. This basically accounts for the memory required to store all the characters of all the words inside our trie, plus the memory used by the recursive call stack, which goes as deep as the longest word, L. And before we wrap up, there's one final absolutely vital optimization detail. A board might contain the exact same word in multiple different locations. To prevent adding the same word twice to our final output list, we simply set the word attribute in our trie node to null the very moment we find it the first time. The next time a path finds that node, it just won't trigger the word found condition. It's incredibly simple, yet it completely eliminates duplicates. So we've completely transformed a struggling, naive approach into a sophisticated, highly optimized algorithm utilizing tries and in-place backtracking. But I'll leave you with this thought. As data grows, optimization is never truly finished. How would this optimized solution adapt, or where might it actually begin to struggle if our board scaled up to a massive 10,000 by 10,000 cells? Consider how you might tackle a board of that sheer magnitude based on the algorithmic foundations you've learned today.